therefore hydrophilic. Water likes them. I don't know what you're doing. Okay, write it in a darker color.
You guys read this?
So, yeah. So the different amino types, there are charged, positive and negative ionic amino acids, and those will be hydrophilic. Some will be entirely nonpolar. There's no difference from one end to the other. And they are hydrophobic. Water likes polar things. And there are some that are just polar within it. It's not ionic. There's no net gain or loss of electrons. But if you look from one side to the other, electrons tend to cluster in different places. And so they'll be polar, and water likes polar things, and it'll come up. So when these react, what's going to happen is, you see... Did I draw that wrong? I did not draw that wrong. You're good. There we go. So these two hydrogens and this oxygen are really attracted to each other. And you have your positive nitrogen and this negative carbon, and these like to attract each other. And they don't like where they're at. They would prefer they'd be more stable if they popped out and formed a different arrangement. So these will join. I'm going to draw this massive thing like so.
While Jack's drawing, keep in mind parts of an amino acid are the amino group, the carboxylic acid, the carboxyl group, right? And that other R group that you have is just going to be any other molecule that you have attached to it. And that's, again, how Smalley mentioned, how you distinguish between your amino acids, right? You have 20 different amino acids that can code for a variety of things. So
yeah. Does anyone remember if an amino is acidic or basic?
Acidic.
Wrong.
Basic.
Basic.
Yeah.
Right.
Try.
How do you know that it's basic?
Good job.
How do you know that it's basic?
Because it's basic.
Well, for one thing, yeah, there's three ways to think of it. Way number one is that it's going to be an electron receiver. It's positive, so it likes to take them in. Do I have that backwards?
Actually, yeah, it's an actual electron donor, actually.
Yeah, these have already reacted, and it's doing the opposite to go back more stable. So it's going to be an electron donor, proton receiver. It wants to tack this extra hydrogen onto
Does
the
anyone
nitrogen.
remember the Lewis definition for a base? A Lewis base is an electron donor, right? Okay. So then a Lewis acid would be an electron receiver. A nitrogen is your best example of a Lewis base. That's like really important to key in on. So that's why amino is a basic structure, because you have your nitrogen that looks like this right here. Those electrons are going to donate, so it's going to be a Lewis base.
Yeah. So one thing I'm just going to point out here is that this has already reacted and given off its hydrogen. So this acid has already reacted, so it'll want to go back to a neutral state. So they're going to act the opposite of what you'd expect. This has already gained another hydrogen, and so it's going to act the opposite of its normal basic attributes. Regardless, these two like to act just with each other, and so this oxygen, that hydrogen will pop off. The electrons will share, and you'll get water coming off, and a peptide bond will be formed. So this bond here is really, really stable for this. Proteins don't like to break apart much. And so this will pretty much dominate any other bond that it'll encounter.
And how this happens, it's called dehydration synthesis.
Because you have what would make a water, and some of it breaks down, breaks off, and you get a water form.
Yeah.
So water comes out of what's in it.
And it's synthesized. So it comes together, and you lose the water. So dehydration. That's a really important thing to key in on again. And then, so let's say, okay, just really quickly, before we end this part, if that's dehydration synthesis, you have two individual amino acids joined together, releasing the water. How would you take apart these amino acids? You would, if we took out the water over here, what are we going to do over here?
What would you need to even be able to do it?
Add water. So that's called
Hydrolysis.
Say it again.
Hydrolysis.
Hydrolysis, right?
Right. And one thing that you're going to notice later on in pre-AP bio is when you're undergoing, what is it called? like when you're getting energy for the cell.
Cellular respiration.
Yeah, cellular respiration.
Cell rep.
There's also hydrolysis that goes on, where you take a water, bring it in, and break something apart to get energy.
But that stuff is for memories, okay?
That's for another day.
All right.
Any questions about anything I've covered with the structure of DNA, transcription, translation, RNA versus DNA, nitrogenous bases, and proteins, and peptide bases? You guys are all good? I'm going to ask you one thing from the beginning. What's the difference between ribose and deoxyribose? Yusuf.
Deoxyribose has an oxygen taken away from it.
Wait, hold up, Jack. You call him a safe person.
He's right there, and he raised his hand first. Okay, Aisha. I figured you wanted to know. What's the answer?
I said that deoxyribose does not have oxygen
On which atom?
on the second atom.
Correct. And ribose, on the second atom, there's a hydroxide, an OH, or a hydroxyl group, that defines how it interacts with other stuff. And on deoxyribose, there's just a hydrogen. It's missing an oxygen. Awesome. You guys were great. Thank you.